Good afternoon. I hope you're all full of cookies and soda, and you're ready to see weaponization of cellular-based IoT technology leveraging smart devices to gain a foothold. My name is Window Snyder, and I am on the Black Hat Review board, and I'm very excited to introduce you to Daryl Hyland and Carlotta Bindner. Daryl Hyland serves as a principal security researcher at Rapid7, and Carlotta Bindner is a lead product security researcher at Thermo Fisher Scientific. Please welcome Daryl and Carlotta.
Thank you very much. So let's go ahead and get started. So I want to do a project introduction. So where did this project start? So me and Carlotta started working on this probably about two and a half years ago. And this was initially driven through observation. Both of us work on IoT assessment, pen testing, those type of things over the years. And one of the things we noticed is this growing use of cellular-based technology in IoT. And we really lacked effective knowledge. And there was a lack of real good security testing methodologies that we could actually deploy in the area of testing. So our goal was, let's start digging into this. Let's try to understand what cellular and IoT means, build testing methodologies, and answer those security questions. The two texts we're going to be talking about, or our research focused on, one was NB-IoT. NB-IoT is like half duplex, really high latency. The other one is LTE-M. This one is much faster, lower latency, full duplex. You often see this in devices that move voice, images, video, and much more data. So the focus was, when we started digging into this, when we think about cellular technology, we're familiar with this area is typically encrypted, at least in all current monitor cellular tech. And it's also regulated by FCC. So for us to effectively kind of look into this area, we'd have to build like Faraday cage and follow regulations and all that stuff. So our focus was, let's look at inter-chip communications, the communications that flow between the main CPU and the cellular modules on these devices. In this area, this is typically not encrypted on most of the devices we've actually looked at. And it gives us the ability to interact more deeply with the technology. So as we expanded forward in this research, we noticed that these devices, Internet of Things hardware, the trust relationship of these devices is what we become interested in. What do these devices have access to? What can they gain access to? And we started thinking about this. These devices have access to services, cloud, internet, and even private networks through private APN environments. So what's our goal moving forward and what we're going to talk about today? We're going to target this trust relationship, and we're going to do it by controlling this, controlling inter-chip communication so we can actually control the cellular modules in whole. So now I'm going to turn this over to Carlotta, and she's going to talk to you briefly on how do we talk to a cell module in circuit.
So Daryl talked about the wide view of how cellular comms work. But on the hardware level, there are two main paths for communication between this primary CPU and the cellular module. Those are USB, and when we're talking about USB, we're talking about standard 2.0 high speed that implements basic functionalities of USB. And then UART, Universal Asynchronous Receive and Transmit. On the cellular module itself, there's usually two UART interfaces. One's the debug that you could interact with to like log in usually or see a load screen during the device booting. And then the main UART is actually connected to the primary CPU. Now, when the CPU and the cellular module are communicating, they are using AT commands, which is short for attention. These were originally designed in 1981 for the Hayes smart modem and are still used today in cellular modules. That's partially because they are a nice short text string command interface. These are used for configuring the device to connect to the cellular network, for making those changes for management. You can do diagnostics with those commands as well and update the firmware on the device. And just take a note of the AT command manual screenshots there on the right, because we're going to mention that in a little bit. So there are sort of four categories of AT commands: the test, read, write, and execute. Now, some commands actually will have the ability to do test, read, and write, or only certain, for like actual configuration. You can then ask for that information back, what the current setting is. And then execute commands, we're actually going to use one later in the presentation to make the cellular module perform actions on our behalf. Now, while I did say that there's 4 types, the thing about AT commands, the 3GPP, who it's a umbrella organization that does the standards for telecommunications, only requires certain AT commands for manufacturer to implement on their devices. Usually that's for being able to just connect to the cellular network, make phone calls. But IoT devices use a lot of different protocols, and so manufacturers actually have developed their own specific commands that implement more advanced features, whether that's being able to do HTTP commands, open sockets, which we'll talk more about in a bit. And on the right there, each of them have their own sort of syntax, and you can usually identify them by the prefix. Quectel uses a Q, uBlocks uses a U, et cetera. And this is only a few of the manufacturers. There's even more with their own custom commands. And as I mentioned about the AT command manuals, that's where you can find pretty much all the information about for whatever particular cellular module you're finding. They actually release a AT command manual for that particular module model, and that information to be able to understand like what parameters, what AT commands, and then even like examples of the responses of what you would see by running it would be in that manual. And now I'm going to hand it over to Daryl to talk more about the physical interaction of the device.
Thank you, Carlotta. So now that we know what the process is for talking to the devices, the AT commands, let's look at the hardware part. For us to be able to interact with the cellular module on an actual device, we need to be able to tap into that device. One of the methods I often use to start off with is I do a transposal. So basically what I do is I take images of both sides, I overlay them with each other, and from there I can actually see both sides of the board at the same time. This gives me the ability to see chips, surface runs, vias, and things like that. And then on top of that, we actually get the actual data sheets, and then we overlay the land grid array on the actual device. From there, we can identify things like UART, USB. This makes it much more simpler to know where to target on the board to attempt to find out how to interact with this communication on the board. But inevitably, it doesn't always work that easy. We often run into things that are not accessible. So how do we deal with that? And I know you're looking at the slide, you're going, acupuncture needles, seriously? The answer is true. Here's an example. The way to do this is if you can actually turn the module on its side and see edges of the land grid array, you can use acupuncture needles, insert them up underneath the body of the actual chip or the cellular module, and from there you can actually gain access to the USB and the serial communications. It gets a little more complex. If that doesn't work based on the module, we can actually take the device apart. We pull the module off the board, we use heat, IR, reflow, take it off the board, and then map out our own circuits. From there, this was a test sample as a proof of concept. How difficult is this? How hard would it be? It's actually quite simple. Using land run repair kits, I was able to run runs up underneath here and then use UV set masking over top of her for protecting it from shorting out. We're able to do this, reflow the chip or the module back on there, and from there, we're able to tap into those critical communication circuits that we want to get access to so we can use the AT commands to communicate and control the actual module. The next step is, what if these don't work? And you get into actually digging into the board. I've done this with success a couple times. It's a matter of figuring out where you think the stuff's at, cutting into the circuit board and finding the actual circuit runs and tap it into them on a sublayer of the board. Way more complex, but if you take your time, dig into it, you're able to actually accomplish this and tap into the critical circuits that you can get for communications to these devices. So now that we know how you talk to modems and we know how you actually get into hacking the hardware and figure out how you do it, we're going to go ahead and combine those things. I'm going to turn this over to Carlotta. She's going to talk to you about the mechanics of weaponizing over UART.
Thank you, Daryl. So this diagram provides a sort of simple view of what a setup for connecting to UART and being able to issue commands to the cellular module would look like. We actually terminate the runs between the primary CPU and the cellular module on UART and can place ourselves pretty much replace the CPU with our FTDI device. And what that looks like on this device, we've identified the TX and RX. In the middle screenshot there, we've actually put wires on 2 locations on both TX and RX, and then we cut the traces in between those, cut those traces. Then you can actually hook up wires to a breakout board. You'll notice that there are actual switches in the middle there of that breakout board, and that allows us to control the flow of communication between the primary CPU and the cellular module. So when it's on, the device could continue to behave as it was intended, and when we turn it off, we can actually take control and start issuing AT commands. Now, I mentioned that manufacturers provided a plethora of commands for HTTP and opening sockets. And as a result, we actually created a set of various scripts to be able to use those AT commands and recreate tools that we would normally use on pen testing, including a port scanner, HTTP proxy, and then I will be showing a demo of an S3 bucket scanner that has been implemented using AT commands. So right here, I'm actually in a serial terminal. I'm just waiting to see that the module is actually up and responding. It's saying ready. I issued an AT to say, and it responded with an OK. So this script actually will accept bucket names, an individual bucket name, or a list of files, a word list. You can configure extensions for different files you might be looking for, the S3 endpoint that you would be targeting, and then the serial port that you're connected to on your laptop. Oh, and I also included an assume on so that it will wait for a ready, but if your device is already on, it will just hang there for a while. But by being able to actually create these tools with AT commands, we can replicate and go after the internal resources on the network that the device is actually connected to, or internet-facing hosts as well. And as you can see, it is iterating through its targeted research cell bucket, which is an S3 bucket that was set up specifically for this, instead of obviously targeting anybody that could get us into legal trouble. And all of this information is actually being saved into a file at the end. We've found flag.txt on that S3 bucket, and then it saves to a JSON file that you can then parse with JQ. So having the ability to recreate tools with AT commands is wonderful, although there are limitations. Due to the simplicity of AT commands, more complex authentication and loading can sometimes, exchanges can become more difficult with AT commands. So we turn to PPP over UART. This allows us to actually establish network access through the cellular module. The cell module becomes a server, and we run a PPP daemon, and we are the client. You actually get assigned an IP address, and you are effectively surfing the internet via the cellular module. And the ATD star 99 pound was that execute command that I was referring to earlier in the talk. And to be able to make this a little bit easier, because the actual setup of PPP on your system can be problematic at times, and there's a lot of different flags, I actually created a simple Python script that I'm going to demo here, and actually run a tool through the cellular module. Now, in the demo, I did include a little bit of showing that currently we have no PPP0 interface, and I am connected to a wireless network at home, and I've got an IP address. I also included running a ping command against Google, and you'll understand in a second, in a little bit here, why. It was about 43 to 46 seconds time for the ping command. So this is the cell PPP script. It accepts the FTDI interface that you have, the baud rate, and then the APN that the device that you want configured for the cellular module. And now it is working on just making sure the module's ready, that the ATE0 is actually to make sure that all the commands are printing out so you can see everything. And it's establishing that PPP0 interface and a connection. We have been assigned an IP address, and we also even have DNS. The script will then change that to our default route. I've disabled my Wi-Fi. So I no longer have a network on my home network, but I do have a route via PPP0. So let's run that ping command again. I think it's about, once it pops up, it's like 67% data loss, packet loss there. So unfortunately, the thing about it is it is sort of, it did improve over time as it continued to run. And here I am running Not So Secure's AWS enum script from their cell enum repo. And this is getting sped up because the amount of time that it actually took to run this tool was about anywhere, I ran it a couple of times, it was between 40 to 45 minutes to run this over PPP over UART versus on my home network when I ran it, it was like maybe 3 minutes. But it does work. I mean, if you're patient enough and ready to, I guess, go grab a cup of coffee while this runs, you can actually perform enumeration of cloud hosts, or run any other tool through PPP over UART. So what are the pros and cons of using UART and the AT commands over that? It's a lower level of effort, as you're going to see when Daryl starts talking about USB. PPP over UART is available, although only in some cases. Some cellular carriers do actually, they've dropped support for PPP. So the slow speeds and the limited data throughput, there is the alternative of being able to do USB, and I'm going to hand it back over to Daryl to talk about weaponizing USB.
Thank you, Carlotta. So as you know in the presentations, there's two communication channels. There's serial and there's USB. Typically on these devices, even though they're available on the modules, they're not both implemented on most products. The product's either going to use one or the other for its control and communications. So in this case, the device that we were doing research on is a camera system, and it utilizes USB. So as I started thinking about this, is like, how do I even interact with this in any real usable manner? What kind of technical issues am I going to run into? And where do we even start to do this? So I went out on the internet, read a lot of stuff, tried to figure out what this means. There's things we have to deal with. Often with USB communications, there may be a termination or impedance matching resistors that are in the circuit. So if you go to start modifying the USB circuit, you need to take those into consideration. You also have trace length skew. Between your opposing lines, D plus and D minus, you can't have one too longer than the other. That's skew. The actual protocol for USB 2.0 is way tolerant. So you can easily do this without much problem. If you're running it with a device with USB 3.0, it's way more complex to stay within the skew distances. We also have trace branching. So if we're going to modify a circuit, we have to take into consideration of not leaving any traces on the board that aren't going from one point to the other. This would cause signal reflection. So the signal degradations you got to deal with is impedance matching, crosstalk, noise, and signal reflection when you start modifying the actual circuits. So I started researching, like, how am I going to do this? How am I going to interact with the circuit? So I found this Texas Instrument device. It happens to be a multiplexer. It's a 1 to 2. In our case, we're going 2 to 1 in this particular case. And I thought, well, there's good manuals on this chip. I could develop my own board. A little more research, I found out there was a pre-assembled board coming out of China. This board's about the size of a quarter, which is actually freaking humongous in the world of electronics. And trying to patch that into a device could have its own problems. But it did solve some of my electrical requirements or electronic requirements. So then I started thinking, how do we effectively splice this into the actual circuit? So this is what it looks like electronically or electrically. We have the cell module. We have the CPU that's part of the device. We want to drop this multiplexer in place. What we're trying to accomplish is the ability to switch host. We want to switch the host from the CPU to our laptop. And as this part of this targeted attack, the goal is to take advantage of the trust relationship of this hardware. This hardware, when it comes up, it goes through its entire authentication process, through its APN. It may authenticate out through a VPN function. It may authenticate in the various cloud services or functionality. So we want to be able to take advantage of that. So the goal is we stay on CPU, let the cellular module and the CPU carry out all the authentication and negotiation for us. Once we think that is accomplished, we want to be able to switch the device over to the laptop through this multiplexer, take control of the circuit, and actually use it to route our data through. So here's the actual board. This particular board, we got to watch out for abandoned lines on the device. So you see the USB trace that we have there. So we cut these lines at this report. We remove them completely out of the circuit. Then we come over here and we want to put the wires in. We need to keep the wiring attached to our device the appropriate length so we don't have skew issues causing errors in the actual circuit. So once that's done, we take the device, and now we need to wire the device in here. So we have the one switch, the S. The S is used to switch from line 1 to line 2 and back and forth. The OE is taken to ground to make sure to power up the device. When that OE is put to ground, the actual multiplexer device will come online and function. So the goal is here, wire this whole thing in. So we put a large mezzanine header on the device so we can lift it further off the board because everything needed to go between the cellular device and the actual main circuit board of the actual device. So from here, we connect the wires into our multiplexer. We connect power up. We connect the wires down at this point. So my initial goal during this process was let's not screw around with line 2 of the USB. Let's just get this stupid multiplexer actually working in the circuit. So I wired it in this way, powered the unit up, let the CPU stay on, route all of its traffic through the multiplexer, and the device came up running. It authenticated out to its services, started sending images and pictures, fully functional at that point. So the next goal was we need to tap into this multiplexer and see if we can take advantage of this. First thing I did was I got one of these pre-built USB plug units, and I wired it into the circuit. I hooked D plus to D plus, D minus to D minus on the two things, and I kicked it off, and nothing happened. It did not work. It was noise, noise, noise. So I put a USB inline sniffer on this and examined it and was constantly trying to negotiate down to a lower speed, and threw nothing but errors. So I did some research, and the common factor for that error is you have D minus and D plus swapped. So I'm not sure these lines were actually marked right, so I said, screw it. I threw that in the trash. I came in and I just wired a plug into the device. I know the wiring standards on the plugs and the color coding. I went ahead and wired this into the actual circuit. We were able to plug it up. I put it through a USB inline to my actual laptop. When you connect in with this wire, you have limited length. Typically, USB standards and it goes out pretty far for cables. But if you hook a large cable onto a cellular device module directly like this, you'll load the circuit down pretty quickly if you don't keep it short. So we put the USB inline sniffer in line there. So now let's throw a demo and show you what we can do with this. So as we kick this off, let's annotate these. That's my serial console, so I can see if it comes up ready. My multiplexer and my USB capture, so you can see when I whip it over to my laptop, you can see communications taking place. At this point, I'm not connected to any network services, so we get network unreachable. I also run this particular command on my Mac, and we can see that there's nothing on there that would indicate a cellular device. So let's go ahead and have some fun. So we power up the device, it goes to ready mode. I send an AT command to it just to say it's okay. Let's go ahead and throw the switch and see what happens. We throw the switches, it goes over to line 2. Instantly, we got data, and it gives us a network interface card on this device. So now we're routing an entire Mac laptop through this IoT device via its USB, utilizing a multiplexer in circuit. We can ping. If we jump over and actually look at the USB on the device, we can see we have an EG91. So let's go ahead and throw a little salt into the wound. We're going to carry out an SSH Metasploit brute force attack against the device through the IoT device's cellular functionality. So we're going to go through 4 attempts from here. Last one will be the right password. It throws us up a session in Metasploit. We see we have a session enabled. Let's go ahead and utilize that session with Metasploit. Now we're connected into the device. So now we have our entire laptop routing through this IoT camera by leveraging a multiplexer in circuit to give us the ability to do that. So this device has the ability to connect out. So the critical way to think about this, right now on this particular test device, we're on the internet, so we have access through the internet. But if we were dealing with a IoT device that utilized what was known as a public APN, or private APN, and it connected out to an internal network or on some kind of internal services, we would be able to leverage this device to route everything through. Now, the functionality on the USB on this LTM device happens to be ECM, which is Ethernet Control Model. It's basically an Ethernet port. That's what it is. And it works. When you plug in any operating system, it's going to detect this no different than if you went out and bought a cellular modem, plugged into your device. It's going to detect that as an actually network interface card. So the complexity, hardware hacking. You're going to have to go in there, take things apart, cut lines, solder in things, make changes into that. Some restrictions. Not all devices have ECM capability. NB-IoT devices, some of them may not do ECM. Even if they do, there may be high latency on some of the devices that you may have to deal with. But nonetheless, and you can see this is like way more faster than point-to-point protocol through the AT side, the serial side. So with that said, we need to talk about some security mitigation strategies. So I'm going to turn this over to Carlotta, and she's going to address a few of the ideas we had. I do ask, though, if you have any ideas on your own, catch us afterwards and share that with us. We're open to how do we fix this problem or at least mitigate it.
So what can manufacturers of devices do to hopefully mitigate some of the risk around this? I mean, yes, you do need to have physical access to a device, but there are ideas of supply chain attacks, among other things. Tamper protection, especially case triggers, in our opinion, would be the most effective versus epoxy potting, partially because if you're patient enough and you're determined enough, epoxy potting can be undone. Case triggers, usually either an electronic or a physical case trigger. If you open the device, it would make the device dead. Disabling USB or UART. As Daryl had mentioned, usually the device is only using one line of communication, either physically or through the software. Terminating the other one, preventing it from being used to communicate, would be another possible mitigation. Encrypting inter-chip communications so that we can't see them as easily. And then on the cellular provider side, APN monitoring, cellular bandwidth usage, and behavioral monitoring. Your cellular camera should not be, or any other IoT device shouldn't be scanning the internet or internal networks. Internal network security monitoring for the, for the actual device provider, network segmentation. And product security, because you can make these implementations, but sometimes they don't work as you thought they would, or somebody may be able to find a way around them.
Thank you. So kind of one last comment, well, a couple different ones, not one that's on this slide. So in our demos today, we were using EG91, which is a quick tell cellular module. By no means is any of this meant to be against them. This works on almost every NB-IoT or LTM module that we've actually looked at. So it isn't against any specific vendor or product in that case. And the one last comment I want to make, we've been talking about taking this device and weaponizing it, use it to gain a foothold into its trusted resources, whether that's cloud services, internet services, or happens to be targeting through private APNs, internal networks, VPN connections out there. What about if these things in the supply chain, remember, there's two channels. There's USB, there's UART. One or the other is used, rarely or both of them. I've never seen a device where both of them are used. These devices can easily have an implant put into them, small computer system, that would open these things up to a nefarious activity, being able to phone home and take command and control functions, do surveillance, remote triggers. So it's something to seriously think about from that perspective. We were talking and researching one way, but I had some people mention this to me that I hadn't really thought about it. You can go back the other way too, that we need to be concerned with. So just a couple points to make. Cellular module AT command structures are easy to construct tools with. These AT command and manuals are widely available. There's a lot of data out there. It's easy to construct and take over these devices and control them with AT commands. On top of that, we got trust relationship issues we need to be concerned with. These devices have access to something. That access is a trust-related access, and it could be used to target that trust. And with those two things said, how do you mitigate a threat when the attack is how the device works? We're actually leveraging the normal functionality on these devices. How do you protect yourself from the normal functionality being used against you? Often this is going to be generally good security practices that you need to consider. These devices should have limited access. That means if they're going to connect out, they shouldn't have shared resources between all the devices. Let's say there's 10,000 cameras out there. If each one of those have their own data, but for some reason, being it's a machine-to-machine communication, you lost the factor of trust, and now one device could potentially get to other devices' information. Or if it's a private APN, it can gain access. It should only get access to what it should have access to. A single device, a single port to move data back and forth, and not be able to do InMap scans or scans on the inside of your network or carry out brute force attacks. Segmentation is the way to go there. Also, put segmentation to prevent some of this stuff. And then again, monitoring. Where can you put monitoring so you can detect changes in behavior for devices that you know what's coming in, you know what it should be doing, you should know what it should be talking to, and you should know generally what the data that should be moving back and forth. And if it's not doing that, you should flag it. So that gets us down to questions. So we have some mics here. If anyone has any questions, please step up and
Yeah, it was quite involved, your unpacking and then doing the direct soldering connections. What were you trying to simulate on an attacker? Because I assume an attacker coming in is not going to have physical access to your IoT device.
Our goal is not to simulate an attacker coming in the device. It's simulating an attacker having the device. He could take the device, modify it, whatever that device has access to. If it goes through a private APN and lands on an internal network somewhere, he has the ability to use that device to attack you through it. He has the ability to buy one of these devices and possibly attack the trust relationship in your cloud and various internet services and internal network services that this may attach about. So it's about this device being turned into a weapon, not somebody coming in externally. Now I did mention the external aspect of something in the supply chain where something's planted in there to take advantage of that secondary channel, which opens up a whole big can of worms of possibilities. But in general, it's not attack against the device. It's the device being used to do the attacking.
Got it. Thank you.
Any other questions?
Good afternoon. My question was more along the lines of the device that you use for your test, who was providing that DHCP reservation, those IPs? Was that vendor provided, or was those internal IPs?
In this case, what was being provided is part of the cellular module's public APN access functionality.
Yeah.
So I guess so follow on to that, if you're using a public APN, right? So T-Mobile, Verizon, AT&T, whatever, we have no visibility into their IP range and their processes and procedures. The only way that I can foresee us doing is if we own the SIM card and it's our plan and somebody's going through and combing through that data. Have you perhaps coordinated with the vendors to see if they plan on implementing any sort of MAC tracking or anomaly detection to notify customers or something along those lines?
No, we haven't. As the research continues on, which we hope to continue on, the goal is to partner with vendors to test their products, either whether it's public or private APN, and kind of work through the vendor and who they deal with from a business standpoint. I think that's appropriate because there's so many, carriers out there that you have to deal with. How do you get to those? And a lot of these carriers for these IoT devices may be tied into some of the big carriers, but they're weird APNs. They're like IoT Bob, or something. It's often strange that are purely used for IoT type devices. And who do they deal with as the carrier, or do they do anything? So I think working with a vendor and his deployed product would probably be the best approach for us to potentially look at that concept. But thanks for sharing that idea.
Thank you both.
Also, I guess just to add on to that, part of the thing is this is how we're taking advantage of how the device just works.
Yeah.
Like, the CPU and the cellular module are communicating. We're able to actually get in between those two things and be able to issue commands to the AT commands to the cellular module. So we're taking advantage of its existing, just how it works. So it's not necessarily about the different vendors completely, but yes, the mitigations would be something that vendors would have to actually implement.
Awesome.
But also on that, outside of the APN, the device is designed to connect to something, whether it's cloud services or internet services. You as the vendor, as your product, you know those services. If I'm using this to attack your services through your product, which is what we've kind of focused conceptually on, you should be able to monitor that behavior. You're not going to be able to monitor your device being used to attack somebody else.
Yeah.
Right. Okay. Well, thank
That
you
would be
both.
the APN.
I've got a question, two questions, one for Daryl and one for both of you. Daryl, at what point did you figure out that you could use acupuncture needles for a cybersecurity exploit?
The first day I needed them. So first time I looked at the device. So when you look at the cellular devices, I'm always curious. All the cool stuff on most cellular modules is around the outer edge. It's not an internal part of it. So obviously, my concept is I can see this. How do I get access to it? And I had somewhere I couldn't see it, and I actually tried drilling in from the side. I still think that's doable. But in that case, I need more of a precision drill. It was really ratty, drilled out hole, which just damaged things. But yeah, it's like, necessity drives everything.
Crazy. This is for both of you. I said AT commands are like way back with like US robotics modems, V.90, V.92 spec. Where on the internet did you find a complete list of like AT and F1, ATZ, and all those commands that were available that you used on your demo?
So in particular, I had mentioned the manufacturers actually release AT command manuals. So once you've opened a device and you've identified the actual cellular module, whether that's a Lisa or a U-Box Lisa 400 or whatever, you can actually Google like AT command manual for that cellular module, and you will be able to find it. It's there for developers to be able to use. But and then there is a command, although during our previous presentation we mentioned this, there is a command, it's AT plus CLAC, and it will actually print out supported commands for a module, although we did find in some cases some were not actually listed. Some modules would actually support commands and not list them in the output. So But the AT command manuals are really sort of the best place to find the information for that particular module, whatever you're looking at.
Thank you.
Any other questions? Okay, thank you. I hope everyone enjoyed it and got something useful out of this. We're around after this if you want to catch us out here in the hallway, have further questions or input or feedback, please reach out to us.